say, like, if you consider the gradient del as an operator, gradient operator is nothing but a combination of the operators. So let's say if our function has two variables x and y, then the gradient is the operator this comma, or not comma actually, just it converts it into a vector such that the two components of that vector are partial derivatives with respect to its multiple variables. Okay, partial derivatives with respect to its multiple variables. In case, so when you apply it on a function f, it becomes del of f is nothing but del f by del x, or dou f by dou x, and dou f by dou y. Okay, when n is equal to, when it is a univariate function. Okay? In case of a univariate function, yes, similarly you can say, like, in case of a three variable, okay, in case of a three variable one, it will be dou by dou z over here, with dou f by dou z. And in general, if there are, if there are n variables, hello, can you hear me? Yes, and can you see the board as well? Yes. Okay. So this can be generalized. This operator can be generalized for up to, let's say, n variables. Okay. So we'll see the generalization in a short while. But my point that I want to make here is, if it is a, so in case of a univariate function, in case of a univariate function, gradient is the same. So gradient is the same as its derivative. As its derivative. Okay. So derivative of a vector univariate function itself is like its gradient, or you can say gradient of a vector univariate function is the same as its derivative. They are one and the same. Okay. So with this, we can move on to some generalizations now. Any questions, any doubts up to this point in this discussion? You can ask. Okay. In between, I'll just proceed. Okay. So the next point is, let's generalize the functions that we saw to, because, okay, so why do we need to generalize? Okay. For example, okay, so in physics, okay, in physics, in applications involving just physics, Newtonian physics, or normally we like 2 to 3 dimensions suffice. Okay, 3 dimensions suffice. 2 to 3 dimensions suffice. So that's why we have I cap, J cap, and K cap. But when you are performing analysis on data, like while performing deep learning, or uh, working with neural networks. Okay, or any application of when working with data, when handling data. Data has many dimensions or attributes, so we have to go beyond these two or three dimensions, and we have to consider, we have to generalize basically. So let's try to generalize. So in case of physics we have three, in case of data we need many dimensions basically. Okay, so let's start with multivariate functions. Okay, so yesterday we saw the multivariate function f of xy. Consider this xy as a vector. Okay, so what I'm saying is, let's say, okay, instead of xy, I'll take a more convenient notation. Let's say f of x1 x2, f of x1 x2, and let us combine these multiple variables as a vector. Let's say x vector is x1 x2. Okay, so effectively I am operating on a vector. I am operating on a vector. Similarly, in case of three variables, you can have x1 x2 x3. Let's say instead of x y z, because this notation is convenient, I am just using x1 x2 x3. So let the x vector in this case be x1 x2 x3. So now z will be just like operating on a vector. Okay, so now this function, now let's generalize. Okay, going beyond two or three components, we can also have, in general we can have a function which depends on, or you can say a function which has uh, n parameters. Okay, in general you can define the x vector as x1 x2 up to xn, and z is equal to f of x. So this function f maps maps now here we said it maps an ordered pair to a particular values of the ordered pairs to the values of a variable. Here we are mapping values of a ordered triple to the values of a variable. Now in this case we are mapping the values of an ordered n tuple. So in general all of these individually, these are real numbers. These are numbers x1 x2 xn. These are numbers themselves. So we can say that we are mapping an n tuple to the values of a single variable, that is a single real number, that is this. Okay, this is the first generalization. So we are, this is okay, so this is the generalized form of a generalized form of a multivariate function. Okay, now,
Excuse me, sir.
yes, yes,
Sir, can you repeat the last part again? No, sir,
exactly
not
what part?
this F F. Then this I don't understand this symbol. What is that?
This mapping.
Mapping.
Yes, yes.
Yeah, sir.
Okay, so this notation means that we are, so you must have heard of the terminology or the concepts of a domain, codomain, and range. Okay, so basically, do you know this terminology, domain codomain range of a function? No. Okay. Okay. So uh, now all of you must have okay, now this is the non-mathematical example that I'm giving. um, so this is like you are okay, so you are okay, if you have programmed in C, C++, Java, or any such similar language, you pass some arguments to a function and then it returns something. Okay, so for example, you have uh, so this definition is like int f, and this is not actually int. Okay, just try to understand. This is like, okay, it may be like double or something, because we're dealing with real numbers actually, not int. For example, just as an example I'm saying, so you are passing an array, or passing an array to a function, and it returns a real number. So the domain of the function is what the function operates on. The function operates on an array. Function operates on this. Like yesterday we saw, in case of two variables, our domain was a circle. Our domain was x square plus y square minus 9, or something like that. It was a circle, and basically any point from that domain was mapped into a single real number. So that is what this means. Okay, so the function works on an array or on a particular domain, is this vector. Now, because so r means a single real number, r square means this is r square. Okay, this is r square because it has two. Its dimension is two. It consists of two real numbers, so it is r square, or more precisely, it is like taking a cross product of r cross r. Let's say in this case, it is r cube because it has three, and is this belongs to r raised to n in general. Do you get this now? This notation? Yes.
Yes, sir.
Okay. So let's proceed. Okay. Now let's try to generalize the vector valued functions. Okay. Okay. Now our vector valued function r was like this: fti plus gtj plus htk. Consider this as a vector of functions. So consider this as r of t is actually something like this: f of t, g of t, and h of t. It's like a vector because this will help us generalize it. So in general, moving beyond I cap, j cap, and k cap, we can say that, let's say, f is our function. Okay, this was very physics oriented definition. Good to understand at first that this is the displacement, and this is displacement in different along different directions, along the direction of I, along the direction of j, and along the direction of k. Now let's say in general, in case of data, we have the function is f, The argument or the parameter is x that we are passing to it. The variable is x. Okay, and in general it has m components, m f1 x up to f m x. Okay, and we can say in terms of this notation, we can say this belongs to r raised to m. Because it has m components, it belongs to r raised to m. Okay, so this is the generalization of this is the generalized form of univariate okay, so this is the generalization. Okay, the one we saw previously was a scalar. Okay, this was the generalized form of a scalar multivariate function. Now this is the generalized form of a vector multivariate function. Vector multivariate function. Oh, sorry, univariate. I'm sorry. This is vector univariate function. Still, we have only single variable, that is x. Okay. Now, if we want to move on from here to a vector multivariate function, a vector multivariate function, the only thing we have to do here in this is consider x to be a vector, just like we did in this case. Just like we did in this case, consider that x is a vector. Okay. So I'm giving you the generalized case directly, but let's say x can be only x1, x2, or x can be x1, x2, x3. In general, x vector is x1. Okay, we write one below the other normally. Column vector, so x1 to xn. Okay, and it belongs to r is to n, rn. Consider this is your parameter x. Then in this case, the function. Okay, so if x is a vector, then f x, which is equal to nothing but f1 x vector up to fm x vector is also r raised to m. This f, this f is the generalized form of generalized form of a vector multivariate function. Vector multivariate function. Okay, so now here this function f, it maps x vector, which is of dimension r raised to n, to this particular vector, which is of dimension r raised to m. Okay, so we can say that f in this case maps from r raised to n, which is the dimensions of the vector which we are passing as an argument, to r raised to m, that the function returns or gives as an output. Okay,
Excuse me, sir.
yes.
So I didn't understood that where that x1 went. You have written f1 x vector, and why not
Yes,
x1 vector?
x1 is not a vector. x1, x2 up to xn are the components of x vector.
Okay,
Okay, so
okay,
it's like saying other way of writing this would have been, I'll write it in other way, which would have been f of x1 x, or in general, f of x1 up to xn. So f is a function of these n variables x1 up to xn, and here then we would have because this is a vector valued function, this is a vector valued function, so it will have its m components f1 to fm, and all of them will have these n variables to work on, that is x1 to xn and x1 to xn. Okay, any other questions anyone has? Can read the chat now. Okay, any doubts, or shall we proceed? Just reply in the chat. Can we proceed? Okay, then I'll proceed. If any questions, you can stop me. So next point is, okay, so this is the generalized form of a vector multivariate function. Now we have to, okay, so in this case, if I want to find the partial derivatives of a vector multivariate function f, which is defined as it is here, I want to find the partial derivatives. Okay, so in general, again speaking in general, it will be partial derivative with respect to one of these variables, let's say with respect to, so in general I'm writing I, okay, where I goes from 1 to n. Okay, so in general, dou f by dou xi is equal to nothing but, like we saw in case of a vector, derivative of the vector valued function that we saw yesterday, univariate rt, univariate vector valued function. Derivative of a univariate vector valued function is nothing but derivatives of its individual components. So in this case, it will be nothing but the partial derivatives of its individual components with respect to the same variable. That is derivative of f1 x with respect to xi up to derivative of fm x with respect to xi, partial derivative, that is because f1 to fm have all these variables x1 up to xn, and we are just picking one of them, xi. It can be any one, that is x1, x2, anyone, and we take the partial derivative of each of these functions. Okay, so now this is nothing but the partial derivatives of vector multivariate function. Now proceeding to the gradient of the vector multivariate functions. Gradient of vector multivariate functions. Now consider this function. As we saw before, as we saw in case of the gradient, in general the definition of the gradient is, it is nothing but the so each component of the gradient is the partial derivative of a particular function with respect to each of its variables. So if we have n variables, like in this case, our gradient or operator will be defined as by dou x1 up to dou by dou xn, and when we apply it to f, it will be nothing but dou f x vector by dou x1 up to dou f x vector by dou xn. Okay. Now this, no, though I have used this round braces, I I mean to say this is a row vector. Okay, this is a row vector, or this is a vector. Basically, this is a vector. Okay, right now it's a row vector. I can say it's a row vector. So you get the point, right? This is a row vector, one row and n columns, one cross n row vector, basically. So if I expand these, if I substitute partial derivative of vector multivariate function, if I substitute this into this definition here, then my gradient will become my gradient will become this matrix, which is dou f1 by dou x1. Okay, let's, so this is for dou f x by dou x1. So because f has m components, f1 to fm, okay, and similarly continuing to dou f will be the subscript here, dou f1 x by dou xn to dou fm by dou xn. So this entire thing is a matrix of m rows and n columns, and this matrix is also called as the Jacobian matrix. This matrix is called as the Jacobian matrix, and hence sometimes gradient operator in this case, when applied to a vector multivariate function, is also denoted by an operator J to indicate Jacobian matrix. Okay, so whenever you find the gradient of a multivariate vector valued function, you have to find all these partial derivatives, all these m cross n partial derivatives, where m is the number of components of the vector valued function and n is the number of variables. Okay, n is the number of variables of the functions. Okay, so it is m cross n matrix, Jacobian matrix. Let's take an example on this, then it will, and let's see if it is. Yes, yes, ask. Is someone asking something?
Yes, sir.
Yes.
Can you do? can you explain this matrix conversion again? Bro,
Who was speaking right now?
sir, I was.
No, okay,
Sir,
I could not hear you. Can you repeat your question?
sir, can you explain that matrix conversion again from the row and
Matrix conversion. Okay, okay. This is not matrix. Okay, so this is not any conversion of any kind. Basically, see, the gradient that we defined yesterday was the gradient in general is defined as, let's say if you have n variables, a function has n variables x1 to xn, then you take the partial derivatives of the function with respect to each of those variables, and if you write it as a vector, if you make that into a vector, if you make those partial derivatives as the components of a vector, then it becomes the gradient. Okay, so in this case the function f has n variables x1 to xn. So we have n partial derivatives here, starting from dou by dou x1, dou by dou x2, dou by dou x3 up to dou by dou xn. Okay, so if we apply it to the function, what happens? Dou f by dou x1 to dou f by dou xn. So this is a vector. This is a vector. As we saw yesterday, this is a vector. This is a row vector. But if I substitute this formula, this is the formula for individual, you can say individual components of, uh, not components, components of the gradient. Yes, I can say the components of the gradient, basically. So each component of the gradient is a partial derivative. So this is the formula for the partial derivative. That is, this column vector is the formula for the partial derivative. Dou f with respect to dou x1 is substituted by, so this is substituted by dou f1x by dou x1, dou f2x by dou x1, dou f3x by dou x1. So the first row, uh, the first column is partial derivative with respect to x1, second column is partial derivative with respect to x2, and the nth column is the partial derivative with respect to xn. And each, so you, are you getting it, or what? Is it clear?
yes, sir.
Okay, so okay, so let's take an example. Okay, instead of 2 by 2, let's take this example. This will also be easy. Let's take a function of two variables but three components. Okay, so f of, so f is a vector valued function, multivariate vector valued function. Okay, it is defined as, this is the first component 5x1 plus x2, let's say. This is the second component 3x1 square. The third component is 2x1 plus e raised to x2, e raised to x2. This is the function. Now you have to find the Jacobian, or the Jacobian matrix, or the gradient basically of f. Okay, now take some time and try to think about it. Try to solve it on your own as well. So this is nothing but, this is f1, this is f2, this is f3 here. Okay, and Here x vector is x1, x2. We have two variables x1 and x2, and these are three components of the vector. And how will the matrix look like? I'll just wait for a minute, pause for a minute, try to just solve it, and I'll continue in a minute. Okay, you already have calculated it. Good. Okay, fine. I'll solve it here. So first of all, the matrix will look like yes. Good. So it will look like dou f1 by dou x1, dou f2 by dou x1, and extending this brace, dou f3 by dou x1, and the second column will be for x2, dou f1, dou x2, dou f2, dou x2, dou f3, dou x2. Okay. So first one is dou f by dou x1, dou f1 by dou x1. So f1 with respect to x1, x2 is a constant, will become 0. This will become 5. f2 with respect to x1, so it is square, so 6x basically, 6x1. Um, f3 with respect to x1 will become 2. This is a constant, so leave it. Coming to second column, f1, now this is a constant, 0. This is 1. F2 with respect to x2, nothing, 0. F3 with respect to x2, e raised to x2. Okay, let's see what all have you answered. Hemant 516x10 e raised to x2, correct. Chintamani, first row is correct. Pratik, also correct. E raised to x2, yes. Sunil 51, okay, this is just okay, fine. And yes, all of you answered correctly, at least in the chat. So let's move ahead, or you want to take one more example? One more example. Okay. Basically, it's just like you can have any functions here. So fx is let's uh, let's try to do 2 by 3 in this now. Okay, 2 by 3. So in the sense, uh, two components and three variables. So again, keeping it simple, let's say 3x1 plus 5x2 plus 7x3 is one component, and second component is x1 square plus sine x2 plus e raised to x3. Okay, let's keep it simple only. Okay, fine. Okay, try to solve for this. Above example, any questions in this? Which above example? Okay, done. Then yes. Okay. Okay, fine. So yes, 357 2 cos x2 e raised to x3. Yes, I have solved it directly. The gradient in this case will be partial derivative with respect to x1. f1 with respect to x1 is 3. f2 with respect to x1 is 2x1. Okay, now these examples are very simple actually. Let's see in maybe in tutorial when we have more time. There can be combination of the terms as well. Chain rule. I hope you saw the document I uploaded yesterday. Okay, the formulae for derivatives and the product rule, sum rule, chain rule. Okay, so we'll in tutorial I'll give you some examples which will require those rules as well. But right now to understand this concept, I hope these simple examples are sufficient basically. This is with respect to x2 and with respect to x3 is 7 e raised to x3. Okay, so let's move on now. Okay, so the next topic is related with matrices. So let's just revise some properties of matrices and then let's see an example of finding derivatives of a matrix with respect to a vector. Okay, there are different cases that can happen with uh, a matrix. So in this case, if you see, actually, we can think of gradient as we can think of the gradient as taking derivative of f with respect to a vector. Gradient is like taking a derivative with respect to a vector. In this case, this gradient is like taking derivative with respect to because why because uh, gradient is only defined for multivariate functions, and the multivariate part of it, that is the multiple variables that we have, we can define it as a vector, and it's like we are finding a derivative with respect to a vector. So similarly, in case of a matrix, there can be okay, vector is also a form of a matrix. Okay, we can say it's a 1 cross n, if it is a row vector, it's a 1 cross n matrix or n cross 1 matrix, whether it is a row or column vector. So let's first start with, I'll revise some properties of matrices, and we first start with differentiation of a matrix with respect to a vector. Basically, is some combination of it. So let's see. So some basic properties uh, of matrices. A A B inverse is B inverse A inverse. This can be generalized to any number of. So, for example, you have A, B, C up to many such things, many such product of many matrices, and still it will be the reverse of it, basically. That is dot 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 C inverse B inverse A inverse. A transpose inverse is the same as A inverse transpose. Then A plus B transpose is A transpose plus B transpose. If you do it in product, it's exactly like inverse, like AB. What happened? Okay. AB transpose is nothing but B transpose A transpose. If you have multiple matrices in product, then it is exactly the same as the inverse, B transpose A transpose. Okay. Then we had learned about the trace of a matrix. What is the trace of a matrix? Anybody can just answer quickly.
Sum of the diagonal elements.
Exactly, correct, correct. So trace of A is nothing but sum of all the uh, yeah, I can write it in this way. Sum of all the diagonal elements. Okay, I think in the previous term I had used small a, so you can say, so basically the diagonal elements is what I mean, whether row number is equal to column number. Okay, you can use small a or capital A, the diagonal elements. Okay, then eigenvalues, eigenvectors, you know. Okay, then determinant, determinant, we know the how to find the determinant, and this all has been covered in the previous term. Okay, so okay, so let's say if a is if a is 2 cross 2, then determinant is a11 a22 minus a12 a21. I think I had used small letters in this case, but it's fine, you can use capital A or small a. Okay, so in this case I'm defining a as, a11 a12 a21 a22. The previous time I think I had defined the small a11 small a12 small a21 small a22. Minor change in notation, otherwise it's the same. So this is the determinant. Then in case of uh, 3 cross 3, it is uh, you delete that row and that column and take the determinant of the remaining 2 by 2. Similarly, you delete the second ones, and then there is a sign scheme, plus minus plus minus plus minus plus and minus plus minus. Okay. So that is not exactly required right now. For the derivative, what we have is, so let's say, okay, mainly you require transpose and sometimes inverse. So let's say, okay, coming to the derivative part now. Now instead of using the gradient notation, I'm directly using this notation, d by dx of actually let's just use dou by dou x of matrix A, matrix A multiplied by the vector x. A is a matrix multiplied by the vector x. Now note the position that now why I use partial is because only one of it is uh, x vector. We don't know exactly what does the matrix A depend on. Okay, so that's why I use partial derivative. Okay, so this is defined as the answer of this is like it is just like a constant, but okay, so the answer is A in this case. Okay, this is very intuitive. Like for example, if you have d by dx of some constant multiplied by x, then it answer will be a constant. Just like that, if you are multiplying a matrix with the vector and assuming that the multiplication is compatible, like compatible and all, uh, uh, so this is just like applying a transformation to the vector x. Okay, we have studied rotation matrices, rotations. Similarly, there are matrices for translation and other thing. So this is just like applying a transformation on the vector x. So it is equal to the transformation. That is a matrix. I hope you get the point. However, if the vector is to the left, okay, same matrix, same vector, vector is to the left, then it will be nothing but A transpose. Okay. Then the third rule or property is okay, when you multiply two vectors, you will get a matrix. Yes. So here we are assuming that our two vectors have the or depend on the vector x. Okay. So in this case, the product of two vectors u vector transpose multiplied by v vector. Okay, this gives us, so the derivative of this is just like the product rule. If you have read in that sheet that I shared yesterday, only pay attention to the transposes wherever there are. So u transpose plus v vector transpose dou u by dou x. Okay, and with this we can actually solve some things. So the time is almost up, so I'll continue with this discussion about matrices, and we'll also see an example of this in tomorrow's lecture. So I'll take the attendance now. Okay, any questions, any doubts up to this point, you can ask. Okay, then I'll just read out the names. You can answer just like yesterday and then leave. Okay, so roll surname